Hi, I'm Kevin Delphine.
And I'm John Dominguez.
I'm Virgilio De Lara.
And we're going to talk about semiconductor diode circuit analysis.
First, we will start off with the load line analysis. The load line analysis determines the point of operation of the device. Here, we can determine the current flowing through the diode and the voltage across the diode and the voltage across the resistor. Here we have this schematic diagram of the circuit and its characteristic curve. We'll start off by applying Kirchhoff's voltage law to the circuit. So the Kirchhoff's voltage law equation we can derive as E minus VD minus VR equals 0, and therefore we can derive it E equals VD plus ID R times R. Since it is a series circuit, the ID across the diode is equal to the current flowing through the resistor. Then to plug this equation to the characteristic curve, we will set ID as 0. So when ID is 0, we'll have an equation E equals VD. E equals VD will then be the magnitude of VD along the horizontal axis. So E equals VD, so we have here E. Then when we set VD to 0, we will have an equation E equals ID times R. And we can derive ID equals E over R. So here we have the magnitude of ID on the vertical axis. Then it is ER. With the 2 points set, we can now connect them. This line is called the load line. From here, the point of intersection of the load line with the characteristic curve is called the Q point, or the quiescent point, or the point of operation. So from here we can draw a horizontal line towards the vertical axis. Then we can set it as IDQ. Then we can draw a vertical line towards the horizontal axis. And we can set it as VDQ. We can solve this Q point mathematically by using these two equations. But however, it may be time-consuming or cumbersome. To better understand the load line analysis, we have this example. We will use the previous circuit, but now E equals 10 volts and R equals to 1 k ohms. So this is its characteristic curve. So first, we will determine VDQ, IDQ, and VR. We will use our previous equation, which is E equals VD plus IDR, which was derived by using KVL in this circuit. So when we set ID equals to 0, E equals VD, or VD is equal to 10 volts. Then when we set VD to 0, we will have this equation, and substituting the given E equals 10 volts over R 1 kilo ohms, will have an answer 10 milliamps. So this 10 volts, we will plug it on the horizontal axis, which is here. Then we will then plug our ID, the magnitude of our ID in the vertical axis here. This 10 milliamps is here. Then we then connect the 2 points creating our load line. Then the intersection is now called the Q point. When we draw a line from the Q point towards the vertical axis, we will then have our IDQ. Then when we draw a vertical line towards the horizontal axis, we will then have our VDQ. With estimation, we can estimate that our IDQ is approximately or equal to 9.25 milliamps. And our VDQ is approximately equal to 0.78 volts. Then, we'll now determine the voltage across the resistor. To determine the voltage across the resistor, we will multiply IDQ times the resistor, which is 9.25 milliamps times 1 kilo ohm, 1 k ohms is equal to 9.25 volts. Or we can use another equation, which is VR is equal to E minus VD, or 10 volts minus 0.78 volts, and we will have 9.22 volts. The difference between the voltage resist across the resistor depends on the accuracy of the graph given. But this difference can be acceptable.
Another way to solve for a diode circuit is approximation. So first, we should know whether the diode is in a forward or reverse bias. As we can see in this circuit, the diode is in a forward bias. So to know the voltage across the diode, we should know what material is used. Since the material used is silicon, it is 0.7 volts. So for germanium, it is 0.3 volts. And for gallium arsenide, is 1.2 volts. So to know, since it is in a forward bias, there's a current flow in a circuit. And to know what is the voltage across R, we should apply the KVL. So VR is equals to E minus VD. And for the current in the diode, current of the diode is equal to the current of the resistor, because since it is in a series circuit. So, okay. So how about forward? What I mean, not forward bias. It's reverse bias. How can we do that? Reverse bias. Yeah. Reverse bias is an open circuit. Since the diode is going there, so it's an open circuit. And there's no flow of current in a resistor, which is IR is equal to 0. So to know the voltage in a diode in a reverse bias, we should apply the KVL. Since the voltage across the resistor is 0, so VD is equals to E. So let's go to the example. Our example is this. As we can see, this is a circuit. It's a series circuit. So the VD, it's silicon, right? And it is in a forward bias. So the VD is 0.7 volts. VR, KVL. So VR is equals to 8 minus 0.7, which is 7.3 volts. How about current in a diode? So we can solve it by dividing it 7.3 divided by the resistor, which is 22 ohms, where ID is equal to 3.32 amperes. Thank you.
Here we are about to solve parallel configuration using approximation method. In this parallel circuit, we're about to get I1, ID1, and ID2, and the voltage output of the circuit. Since this is silicon diode, and if parallel, you would get the same value. So voltage output is 0.7 volts. In getting I1, we would get the voltage across the resistor and divide it with the resistor. 10 volts minus 0.7 volts over 0.33 kilo ohms will get you 28.18 milliamps. And getting the current across diode 1 and diode 2, we divide I1 into, so since they're both similar and they're both silicon, so 28.8 into will get you 14.09 milliamps. Here we have a series parallel connection. So we would get I1, ID2, and I2. In getting the I1, since it is parallel with this diode, which is silicon, it is 0.7 volts. 0.7 volts over the resistor would get you 0.212 milliamps. In solving the voltage across V2, which is voltage across the 5.6 kilo ohm resistor, we use KVL equation, and it will get you to 18.6 volts, which would we use to solve I2. I2 is V2 over R2. So we use 18.6 volts over the 5.6 kilo ohms. We will now have 3.32 milliamps. And to get the ID2, we use the Kirchhoff's current law. ID2 is equal to I2 minus the I1. We would get 3.108 milliamps in solving ID2.
Once again, this is Kevin Delphine.
This is Calpo Dominguez.
Is Virgilio de Lara.
I hope you have learned something from our discussion. Thank you and God bless.